from the beginning. That is the first slide. Everyone now is good. That I will.
Well, you are in some kind of presentation mode.
Yes.
Two screens, the little one and the big one. This is better. Yeah.
Okay. So a bit about the context then again. The idea is that if you want to have a really precise, or if we want to have like intelligent agent behave in a human-like manner, we need to have a really precise or exact digital representation. So a very nice high-level digital model. But of course, if we use reality capture devices, we go from the real world to the low-level digital model, which is mainly spatial. And through some additional transformations like information injection and so on, we can get this high-level digital model. And when I talked about reality capture devices, of course, why don't we use directly or more directly within this workflow point cloud? So mainly there are three problematic. And the first one is, let's say, point cloud specificities. If we look here at the video, we see some problems of misadjusted density, clutter, occlusion, random errors, or systematic errors, and so on, which can cause problems down the line for using it efficiently. The second thing is, of course, the representation and the structuration. With 3D data, we have various ways to represent or structure the underlying data. And as you can see here, it's a voxel rendering of the underlying point cloud, and each of the 3D data representation and structuration has limits and advantages. So that's something interesting, because the point cloud is actually a canonical data where we can map with more or less success all this 3D data representation, like a 3D mesh or parametric model, a depth map, and so on. And the third problems with point cloud is automation, and that's, let's say, the major one, right? And if I take a classical progressing from acquisition to application, we try and automate in research at each of the steps and have more efficient workflow. Like here, we can see the automation for the UAV to acquire automatically the data. Here we can see trying to have automatic filters to filter noise or things like this. At the registration step, we want to assemble different positions in one common frame of references. This part, which is maybe where I'm the most active, and that would be my favorite if I have to pick one, is segmentation, because I believe a lot of different automation can be solved by having some kind of segment information beforehand. And then after this, we have the classification, where we will group several segments together, for example, to get an idea of and attach semantic information, like a label, like the wall, door, the beam, and so on. Then we have the structuration automation, how to create automatically structure for visualization or processing. And here we can see the nice pottery platform, and I'm really looking forward to what Marcus will be presenting next week, of course. And here we have the application, where in this example, we try to have an automatic, or not an automatic, this is manually for surveyors. They want to extract, let's say, a floor plan based on the underlying point cloud data. And having some kind of automation here would be, of course, nice. So there's three things are challenges toward better integrating the point cloud in this workflow toward high-level application. And the main struggle, of course, for getting this high level is how can we integrate semantic and knowledge within this data set. So what's happening today is that we have a point cloud as a support mainly, and we will have the expert behind the computer that has knowledge, and he will use the point cloud to extract a product like a floor plan, a mesh, or a simulation. And what we want is to integrate directly this knowledge within the point cloud to have a semantic representation that we can act on directly through automatic reasoning based on information extraction. But the problem here is, of course, how can we extract and integrate this knowledge within this point cloud for autonomous decision-making system? And let's say the first big direction is given here. It's based on the smart point cloud infrastructure or architecture that address mostly from segmentation to application automation. And the point cloud that you can see down bottom will be ingested by the parsing module that will, let's say, create some clusters and so on, to be fed through the database module where everything gravitates around. So I will first speak about maybe this database module, where we think about how to structure the data and the knowledge underlying it, which is really interesting topic and gather a lot of perspectives from different communities, which is always nice, I believe. And here the idea is, of course, if we look at point clouds, in 99% of the cases, one point does not describe an object in itself, and an object in itself is not described by only one point cloud. So thus attaching a semantic attribute per point is not the most pertinent manner. Rather, grouping elements as a block storage model seems really really nice. And of course, that is of par with all the database management system where a per row insertion is not really efficient. And here the idea of what drives everything is this conceptual meta model, which is driven by 3 layers. And the more you are in the gray here, the more you are far away from the high level model. And here, of course, you are really close to our domain concepts. So the point cloud here is mostly described at the meta model level 0, the generalized SPC meta model. It's mostly the geometry and the attributes. Here it's a layer that makes the interface between the very low clustering or the semantic patches with the domain ontology that we specialize. So basically we formalize domain knowledge into some kind of computer usable thing that can be for reasoning services. And here you can see that the knowledge drives everything through a decomposition between device that is related to the sensor and so on, analytic, mostly extracted from features or things that do not at this step use any domain information and all domain knowledge. What is really nice in this architecture is we have this bijective communication between different how can I say that, let's say level of detail or generalization level, where one point is the smallest entity and several points will constitute a semantic patch. Several semantic patch will constitute a connected element. Let's say that would be maybe the seat of a chair. Several connected elements will constitute an aggregated element. So the seat of a chair, the legs of the chair, and the backrest will constitute an aggregated element, and that will be called a chair through the class instancing. Right, but to get these different clusters, of course, we need to talk a bit about the parsing module that is acting underlying this architecture or infrastructure. And that's based on the Gestalt theory, which states that the world is greater than the sum of its parts, and that relationships between parts can have new properties or features. So here we really want to leverage the human visual system predisposition to group sets of elements. And if I illustrate this here, for us, it's really easy to define the visual patterns of points, right? That make intuitive sense, like symmetry or parallelism or linearity. But here, if you want to create this feature through feature engineering, you can have a lot of problems, not as straightforward. So here, deep learning is much more efficient because it can create feature much more distinctive without so much brain power, let's say. But of course, before going into directly this all-solver solution, we have to check out the underlying data sets. And of course, with point cloud data sets, there are not a lot of really nicely curated data sets with nice labels and representing all the different applications. So that is where feature engineering is better, because you can have this first step toward having a nice set of nicely labeled data sets beforehand, before using any deep learning technique. And here, what is constructing is it is unsupervised in the sense that there is no training data needed, but also in the true sense that it's truly unsupervised, no parameter tweaking. Because if you tweak some parameters, of course, it's supervised in a manner to get, let's say, the connected elements, and then afterward to get a graph-based classification that I will talk a bit more afterward. So if we look at that on this data set, you can check some results here, and basically the idea is to use the predisposition or let's say the planar dominance of scenes, and then to find and extract some kind of topological pointers between each of those elements to have a graph representation of the point cloud, or the point cloud as clusters, so as connected elements, and we can reason based on this. So we have today more or less 10 million points per minute. but I took the direction of not using the GPUs, so it's all done only on CPU calculation. So you can expect, of course, to use jumps if we switch a bit more. But yeah, what is important here is to see the features. So there is a bunch of local features, mainly derived from principal component analysis, but not a lot. And what is really important when we look at it is all what is context and proximity features, which are really nice and helping, and all the relationship and topology also very, very helpful, like the relationship between host and guest and things like this, which is based on geometrical generalization of the underlying clusters. And all of this is knowledge driven. So basically, we can use directly the graph representation of the point cloud with an ontology and get prediction. And that is also playing with this step, because the ontology or formalizing domain as ontologies using Sparkle or other like all languages, it's nice because you can use automatic resoners that will then create or find new pattern automatically. So let me illustrate this. We have this classified entity through the pipeline that I described, and we have this classified entity where you see the chair in yellow, right? And what we do here then is we isolate the object, the chair, but of course here with the ontology we can deepen the automatically through reasoning the specification. So if we link that to the semantic web with this technology, we can have the formal description of a chair. So here it's in French, but it is in your, let's say, regional language. And the definition is an extension of the DBpedia knowledge base. And basically here what I did is just parse this manually, but we could imagine having some kind of natural language processing to have that automatically, and then create this ontology that describes what is a chair. And you see that we can refine this description with this seat, the backrest, and the legs. So now this chair goes, if you remember, from the aggregated element concept to all the sub-elements, right? So it's an aggregated element, and now we can go through a part segmentation framework to extract all the underlying elements following this ontology. And then with other features like symmetrical features and so on, you get the, the characterization refinement. This is very nice because then you can play with the different representations through this canonical nature to have more information like intersection or proximity to the table and things like this, and extract, let's say, a semantic representation that will be analogous to our visual cognition system. That's what we act on, right? So if I need to answer, if I want to answer this question in a simple manner, I would say that if you want to use that in this high-level model, you need first to have a multi-level conceptual structure, and of course parse the point cloud at the lowest possible level, and be able to plug a domain formalization through an ontology of classification, and of course generating a modular semantic representation for various applications, because else you are too specific or too narrow in your application. And that's where ontologies are really nice, because its interoperability capabilities permit to generalize much more easily than deep learning framework or machine learning framework. And that's an example of an application. Let's say here, surveying back in 2015, I think, a church in France. Combining that with some kind of photogrammetry, we get this reality capture data set. And the idea was the archaeologists wanted to know exactly how many gold or renovated gold tesserae was there. So we developed an application to automatically compute the best point of view based on automatically detected tesserae. And that's interesting because, of course, then she can order the right amount of gold for restoring this these small mosaics. And so that's a digital protection application. And the second possibility, and that's with my current PhD student Abderrazaq, that we do this where we can ingest that in VR application by using, or there is a mistake in application, by using directly, let's say, the semantic attributes, which is really nice, or in an augmented reality application, like you see on the right with a prototype work, which we are working on at the moment. Okay, so now digressing a bit about the Smart Point Cloud in 5 point, why is it nice? Because mostly it's an interoperable point cloud data structure that is, sorry for the slide, that is really important. Then it's leveraged for automated object detection, of course. It provides a large domain connectivity. So if you have a domain formalization, you can just attach it and have your prediction. It's for now unsupervised and very robust variability, but most importantly, it's really modular. So we can, all the blocks that we saw before, we could, let's say, extend them with better performing elements. So here is an example of the application. We select elements like the connected element, and then we can attach the information. Like this is a table of conference. And then we can select other things like isolating all the elements that we do not want to display, for example. And then having all the automatic inference run through. And you can see here all the instance segmentation happening. And then you can select, of course, all the chairs and do some bunch of operation on it and have the classification display as well. So it's also nice to have like an annotation tool to get really fast data sets, annotated data sets. So what would be, let's say, the future direction that I would think of right now? So the first off is, of course, defining powerful AI agents that can use that is a nice direction. The second thing is increasing generalization and specialization is really important. Of course, it was tested in the context of a PhD thesis, so you can imagine it's always limited to a bunch of things that you have in mind when you create this research. The third thing is, of course, having some kind of dynamic integration, so temporal integration, and a better level of data management that is not too grid-like structured, and enhancing the unsupervised segmentation. That's what I'm working on right now, and I will show you some example and the classification as well, and of course integrating more natural processing like language parsing or things like this. So here are some examples of the unsupervised segmentation, where you can see that it's really nice and it generalizes quite well to different scenes with different varying density and so on. And here is another example with other possible scenes. So that is really encouraging. And here, but I think Pierre Allier will have much nicer things here about the 3D modeling. So basically using the segment information directly to model, and you can see how nice are the trees here. To get an idea of the performance, the point cloud here is 100 million of points. And you get these results, the segmentation run under 10 minutes and the modelization run for 300 seconds. Exactly. The topology is totally wrong and messy, but I like it. It's quite artistic, let's say, at this point. And of course, I want to leave you with this to see all the depth that we can use point cloud with. And here is this fun experiment playing with in real time different point clouds and setting them inside one another to see that we can really access a very nice possibilities if we can, of course, fix some of the challenges that I expressed here. And that is a good news for researchers because there is a lot of work and a lot of place for us to do some nice stuff. Last thing maybe is if you want to contribute to a special issue, here there is one automatic feature recognition from point clouds where we aim at gathering targeted to feature extraction and recognition and things like this. It's up to the 30 September. If you have nice research work you want to submit, please do so. And that's it. I hope it was fluid enough and that I was straight to the point. Sorry for all the problems.
Perfectly hearable in the second part, so that was a big improvement. Thanks for presenting. Are there any questions from the audience? Quick questions. Any questions? Okay. Please let me know if you have any questions. If not, we try to switch as quickly as possible to the second presentation by Robert Foute. We will look at indoor point clouds. One more attempt. Are there any questions?
So I see one question. So what database infrastructure do you use? So here is using PostgreSQL and PostGIS for the database module. So actually relational database for all the point cloud storing, but the PG Point Cloud extension really help you handle a big amount of, or let's say large scale point cloud if you have this block storage model vision.
Okay, Florent, thank you very much, and sorry for the interruption by switching to a different video platform. I hope the audience could catch the main message of the Smart Point Cloud approach. I would now like to give the floor to Robert Fouten, who will give the second presentation on indoor point cloud.